Hi statisticians, this is section 8.2. So essentially this is almost the exact same lesson as the one that we did last time in section 8.1, with one pretty significant difference. This time we're going to assume that sigma, the standard deviation, is not known. So last time we were estimating mu when sigma was known. This time we're estimating mu when sigma is unknown. Now, just to kind of give you an overview of how this is going to go, it's going to be the exact same process. We're almost even going to use the same formulas. It's going to be the same process, but with a different distribution. A different distribution, which really just for us means a different table. So you'll notice if you flip to the back of this note packet, you have a table on page 6 of this. This table is not our standard normal table that we've been using, so it's not the table for z's. It's got a couple other figures on here. It looks like the standard normal distribution, but it's actually a slightly different one, and we'll be able to use it to find right tail areas, left tail areas, and two tail areas. But just so you know, there's a different table in the back that we're going to be using today, and also you're going to need to use that for the rest of this chapter, so you might want to mark that one somehow. It's in your formula sheet as well, so you don't really have to rely solely on that one. Okay, so let's start with a little warm-up. From last time, we know that the margin of error for a C confidence level, and remember, usually the C is either 95% or 99%, but there's actually several other confidence levels that we can use, just like usually we do 95 or 99% confidence level, is given by E for error equals Z sub C. This is called our critical value, times sigma, the standard deviation, over the square root of n. So there's this formula that we'll be using to find the error. So let's use it. Let x be a random variable with a normal distribution. This is important. And standard deviation sigma equals 1.19. Suppose you have a sample of n equals 7 values with sample mean x bar equals 46.14 and find a 99% confidence level for the mean mu. Okay, so what we know from last time is that a confidence interval looks like this. We start with our sample mean, we subtract the error on one side, and then on the other side we have our sample mean and we add the error. It's basically saying, like, starting from here we do plus or minus whatever error we find using this formula. That's where our population mean will likely be. Now, it's not a definite, like we don't definitely know that our population mean is in this interval, but we'll be able to say that we're 99% confident that our population mean is somewhere in here. So we're going to plug in almost all of these values. We'll plug in a value for x bar. We actually have that one right here. We'll find a value for E, so we'll plug that in. Same thing on this side. We'll plug in a value for x bar. We'll plug in a value for E. The one exemption here is mu stays mu. We do not plug in anything for mu. So as I said, we already know x bar equals 46.14, so we'll just directly plug that in just a couple of minutes here. Now we have to find E, the error, and that's going to be our plus or minus on either side here. So E equals, now Z sub, and then this is our confidence level right here, that little subscript. So in this case, we want to find a 99% confidence level, so I'll put Z sub 0.99 times sigma, the standard deviation, over the square root of n, our sample size. Now, before we plug anything in here, I do want to point out this problem has a couple of important phrases. First of all, it says that x already has a normal distribution, and that is really important because this is not a very big sample. Our sample is only 7. That's a relatively small sample size. Small enough that we need for our distribution already to be normal. Now remember, 30 is kind of that tipping point. As long as your sample is bigger than 30, we don't really care so much about this whole normal distribution thing. But if you have a very small sample, like n equals 7, it's really important that they tell you that your random variable already has a normal distribution. So this phrase, it's easy to kind of like gloss over this, but it's actually really important that they did say there's a normal distribution here. Okay, so if you remember from last time, we had this table. Your notes last time looked like this. There was a table in the section 8.1 notes, and it gave all of these critical values for the different confidence levels. And so again, oftentimes we use 95 or 99, but there's this entire list of all these other confidence levels that we can use. Now, for 99% confidence, our critical value is 2.58. So we're going to plug that in for this, 2.58. And now sigma, our standard deviation, well, we're given that that's 1.19. So 1.19 here over the square root of n, just using this formula, and n is 7. And again, pretty small sample size, so it's good that they told us that we were already starting with a normal distribution because that is necessary here. Now, let's round this to 2 decimal places if necessary. When I throw this into my calculator, I find an error of 1.16. So that's going to be my plus or minus on either side here. So I'm going to plug that into this formula. Okay, everywhere I see x bar, I'm going to put 46.14 minus, and now here's my error, which I just found, 1.16, is less than, I'm just reading through this thing, is less than mu. Now I do not plug in anything for mu. Mu stays mu. Mu is the population mean. Is less than, and now I've got x bar, which is 46.14 plus that error again, 1.16. And so I'll just clean this up. 46.14 minus 1.16 is 44.98. So my interval is going to look like that. And then on the other side, 46.14 plus 1.16 is 47.30. And the way that we typically read this is, it's a little bit weird. This is something called a compound inequality, where you have like 2 inequalities in one statement, 2 less thans or less than or equal to. The way we usually read it would be mu is between, and then in this case, 44.98 and 47.30. That's how we would read this phrase. And actually what we would say as the answer to this question is that we are 99% confident that we are 99% confident that mu is between 44.98 and 47.30. We can never express this with 100% confidence. We will never find what mu is. All we will say is that we're pretty sure it's somewhere between 44.98 and 47.30. Now remember, our sample mean was 46.14, which is halfway between these two values. So this is a pretty solid guess that it would be somewhere between these. But we're just not, we can never be 100% certain that that's the case. Okay, so again, we're going to be using the same process today that we were using in the 8.1 section. However, in the last section, we knew what the population standard deviation was. And so let me just kind of like go over our entire process again here. The whole story is that throughout this course, you were given mu. Like pretty much throughout every single chapter, every single problem, anytime we used it, you were given mu, the population mean. And finally, in chapter 8, we start thinking, well, hold on a second. If all we have is a sample, then how would we really know realistically? How would we know the population mean? And the answer is we probably wouldn't. If you only have a sample, then you'd probably only know the sample mean. Like in the real world, you're not given a nice textbook problem like you are in a statistics class, like where you have a where you have someone writing the problems for you. So, in this section, things get a little bit more real. Like we don't have the population mean, and realistically, we probably also wouldn't have the population standard deviation. So that's where we are now. Our job is to estimate, I'll say, we want to estimate the population mean. But we won't know it for sure, and also we'll never be able to for sure find it. We'll just deal with one of these confidence intervals at the end. Okay, so last time we used the sample mean to find an interval that we are with whatever level confidence that we hope includes mu, the population mean, and we'll do the same thing this time, except we'll use the sample standard deviation, S, to approximate sigma. So now we're saying, hey, we probably wouldn't know the population standard deviation, but we probably would know the sample standard deviation. We probably would know the sample standard deviation, and so we'll just use that. Now, the thing about this is, unfortunately, we cannot take this formula and just say, well, we don't know sigma, so let's just use S. It's not quite that easy. We have to pay for this estimate somehow, and the way that we pay for it is right here. We were using a Z value, the critical value before. Now we're going to be using something called a T value from a different distribution, which is called the student's T distribution. And the student's T distribution it's almost the same kind of a process as the Z distribution. Like that's where this table comes from on page 6. We're going to be like using this to find one of these numbers, and that's going to be our critical value or whatever. But it is a little bit more interesting. It's a little bit more, I don't know, not complicated. There are just a couple of extra steps that we have to think about with the student's T distribution. First of all, one of the really important things to think about is that the student's T distribution depends on the sample size. So like the Z distribution, we really never cared about the sample. You use the same table no matter what. The T distribution depends on the sample size. Okay, so assume that you're starting with a normal distribution and you have a population mean. For sample sizes of n with a sample mean x bar and a sample standard deviation, we define our variable t using this formula. Okay, so that's great. And then we also have one other little definition that goes with this, which is something called the degrees of freedom. Degrees of freedom are just defined as your sample size n minus 1. So if your sample size is 20, then your degrees of freedom would be 20 minus 1, so 19. If your sample size is 50, then your degrees of freedom would be 49. Okay, so note that each sample size will give a different t value, and that's why t itself has a distribution, which is a little bit interesting. Again, this does not happen for z. So here's something to look at just before we get into doing some problems with this thing. On this is black and white on your note packet, but let me clarify. The blue distribution here is the z distribution, the standard normal. So this is the distribution that we have been using, and this is where our z table comes from, is this blue distribution right here. Now, I have a couple of different t distributions written for you on here. This yellow one is where your degrees of freedom are equal to 4, which again would mean that your sample size is 5, because degrees of freedom is just sample size minus 1. Notice it's still sort of mound-shaped. It's mound-shaped, it's symmetric, but it's definitely different than this blue normal distribution. Like, it's a lot shorter, it's sort of wider, more spread out. Now, if we increase our sample size, in this case, our sample size is 21, which makes our degrees of freedom 20. You'll notice this red distribution is a little bit taller. We've got sort of a smaller standard deviation, so this is all concentrated around the middle, just a little bit more. You can see that this red distribution resembles the normal distribution, even though it's not quite there. It sort of has the same shape, it's just the height is a little bit different. So it turns out, if you keep increasing the sample size, your t distributions are going to get closer and closer and closer and closer to the normal distribution. So let's make a few observations about the student's t distribution before we go forward with it. First of all, the distribution is symmetric about the mean, which is 0. This is not different than the standard normal. Remember, the standard normal is also centered around 0. Well, same thing with the student's t distribution. Again, the distribution depends on the degrees of freedom, and for our purposes, we're using degrees of freedom is just sample size minus 1. So whatever your sample size is, just knock 1 off of that, and that'll give you your degrees of freedom. The distribution is bell-shaped, but it's not exactly equal to the standard normal distribution. However, as your degrees of freedom increase, the t distribution approaches the standard normal. So basically, the larger and larger and larger that your sample size is, the more that distribution approaches normal. And also no different than the z standard normal distribution, the entire area under the curve is 1. So a lot of things in common, but they are actually different distributions. So now that we have this different distribution, we're basically going to do the same thing that we did last time to find a confidence level. Although you will see along the way that we're going to make a few small adjustments, and we'll talk about how to use the t table. So finding the critical values is basically the exact same process. So we're going to find a critical value that's going to give us, for example, a 99% confidence level. Now, just to point out, for the z distribution, this is from 8.1, we were just given this table. So these are the only critical values that we will ever need to know for z. Now, the t critical values, those depend on your sample size. So this is going to be just a slightly different, we'll use them the same way, but the process of finding them is a little bit different. So use the table at the end of this packet to find a critical value for a 99% confidence level for a t distribution with sample size n equals 5. Okay, and the hint says you'll use the row corresponding to the degrees of freedom and the column corresponding to the confidence level. For right now, we're going to ignore the rows that say one tail area or two tail area. Okay, so let's think about this. If n equals 5 and the degrees of freedom are equal to n minus 1, then the degrees of freedom for this particular example would be 4. So here's what we know. We've got degrees of freedom equal 4, and we're looking for a 99% confidence level. Okay, so taking those two values, let's flip to this back page, and you'll notice there's a little slash here, but this kind of shows you how the table is laid out. The degrees of freedom are all down the left column of this table. So this left column gives you the degrees of freedom. Now for us, that problem just said the degrees of freedom are 4. Oops. Degrees of freedom are 4. So we're going to be looking only in this row. Only in this row. And now across this column, the C is the confidence level. C stands for confidence. So this row tells us our confidence level. And we wanted a confidence level of 99, so I'm going to come over here. 0.99 is that 99%, so I'm looking in this column. And that brings me right down to 4.604, and that's going to be my critical value. Now, I'll write that in just a second, but let me point out one quick thing that's like a little bit of a potential pitfall on this table. There's also 0.999, but 0.999 is a confidence level of 99.9%. So there's 2 decimals here that start with 0.99, and just make sure that you're using 0.990. 0.990 is 99%, 0.999 is 99.9%. So we're using this critical value. So again, degrees of freedom and then confidence level, and when we line those up, this is our critical value, 4.604. So that's the answer for this one. Our critical value for a 99% confidence is, 4.604. And we use the same notation as we did for the Z, so we put a little subscript and then your confidence level there. One other really important thing to note, I would highlight this if I were you. If the degrees of freedom that you're looking for are not in the table, use the closest smaller degrees of freedom value. So what I'm talking about there is, again, if you look at the table, remember the degrees of freedom are along this left column, and everything from 1 up to, let's see, 1, 2, up to 30, every single value is accounted for. But after 30, we start skipping. So 30 and then 35, now we're counting by 5s. Well, once we reach 50, now we're counting by 10s, 50, 60, 70, 80. Then 80 jumps to 100, 100 jumps to 500, and 500 jumps up to 1,000. So let's say if you were doing a problem and your degrees of freedom are 92, if you have degrees of freedom 92, well, 92 is not in this table. You're going to always go to the smaller value. So always go to the next smallest value. Even if your degrees of freedom were 499, which is in here and very close to 500, you're still going to jump back on the table to the next closest smaller value. Only if you have to. We'll mostly deal with degrees of freedom up here on the table where you have everything, but just in case you were to encounter that, you always go to the smaller value. Okay, so back to page 3. Now, when you do not know sigma, we're going to follow the exact same process that we did in section 8.1 and also in the warm-up to find the margin of error. And then we'll create our confidence interval from that. The 2 changes that we have to make are that now, since we don't know the population standard deviation, this is going to become S, the sample standard deviation. And since we're making this change, we have to pay for it here. Instead of using a Z value, we're using that T value from the student's T distribution. So these are the 2 changes that we're making when you do not know your population standard deviation. Other than that, the process is exactly the same. So these are the same steps on the next page that pretty much came right from your 8.1 packet, but just modified a little bit. Suppose that you have a simple random sample of size n. Now we have the sample mean and we have the sample standard deviation. If x already has a normal distribution, then great, we really don't care about the sample size. But if x has any other distribution, or if it doesn't directly say that your distribution is normal, then we still have to have that 30 or larger. That's kind of like the appropriate sample size, that things get close enough to normal that we really don't care. If all of these conditions are met, we're going to use this new error formula to build our confidence interval. Okay, so let's try it. Suppose an archaeologist discovers 7 fossil skeletons from a previously unknown species of miniature horse. Reconstructions of the skeletons show that the shoulder heights in centimeters are as follows. So here is our sample of 7 data values. For these sample data, the mean is 46.14, so sample mean, of course, because this is not the entire population. And the sample standard deviation is S equals 1.19. Now, this is a really important statement here. Assume that our distribution is approximately normal. That's important because a sample size of 7 isn't big enough to overcome it if it's not. So it is important that we include that information. Find a 99% confidence interval for mu, the population mean. So when it says to find a confidence interval, it's talking about this x bar minus e, and then mu between that and x bar plus e. So basically the sample mean plus or minus the error. Now, normally, I mean, you probably kind of already know what we're going to do in this section because it's the section about not knowing sigma. But in general, you'll have to figure out which situation you're in. So here's sort of like a little decision tree. The question that you'll always ask yourself on these problems is, do we know sigma? If the answer is yes, if you do know sigma, the population standard deviation, then you're going to use z. You'll use the z distribution. You'll use all your z formulas. You won't deal anything with t if you already know sigma, the population standard deviation. This was section 8.1, was this entire branch. This is what we did in the last section. Now in this section, the answer is no. We do not know sigma. And if you do not know sigma, then you use t, the student's t distribution, the one that we just went over. Okay, so let's just get all of our values together now that we know kind of what situation we're in here. So first of all, it says, suppose the archaeologist discovers 7 fossil skeletons. So that tells us that our sample size is 7. Also, since we're going to be using t, we need to know the degrees of freedom. And remember, degrees of freedom, that's just n minus 1. Well, if n is 7, then n minus 1 is 6. So our degrees of freedom are 6. So in this case, if we go down our little decision tree here, do we know sigma? Well, no, we know S. So we're in this branch, and we're going to use t. The formula that we're going to use for the error then is going to have the t value, the critical value with t, and then times S over the square root of n. Okay, so it's not quite as easy as the z table where we just look through a list of like 10 critical values. For the t distribution, it all depends on this degrees of freedom. So I'm going to flip to that table in the back. Oh, and there's actually one other thing that we need, which is this confidence level. I'm going to flip to that table in the back, and I'm going to take with me 2 pieces of information. First of all, I want a 99% confidence level, and my degrees of freedom are 6. So going to this table, let's come down to Degrees of freedom, remember that's along this left column. So degrees of freedom is 6, which tells me I'm looking only in this row on the table. And my confidence level that I want is 99%. And so again, even though there's 2 decimals here that start with 0.99, 99% is 0.990, not 0.999. So I'm in this column, and my critical value is 3.707. 3.707. So T sub 0.99 equals 3.707. And I'm going to plug that in here for this critical value. So I'm finding the error. I'll start with my critical value for T, which we just found to be 3.707, times the sample standard deviation, which I'm given 1.19, over the square root of n, the sample size, which is 7. So 3.707 times 1.19 over the square root of 7. Let's round this to 2 decimal places. I find 1.67 for the error. And now I'll plug that error in everywhere I see an E in my confidence interval. So x bar minus E, and then mu, and then x bar plus E. Okay, so everywhere I see an x bar, that's the sample mean. I'm given 46.14. Minus the error is 1.67. And then I've got mu. Remember, mu always just stays mu. You don't plug in anything for mu ever. 46.4 right there again for the sample mean. And plus 1.67 for the error. And then I'll just clean this up for my final answer. 46.14 minus 1.67 gives me 44.5. And so I find that mu is between 44.5 and, throwing that into my calculator, 47.8. And now again, I can't say with complete certainty that our population mean really is between 44.5 and 47.8, but what I can say is that I'm 99% confident that the population mean is between 44.5 and 47.8. 99% confident. Okay, before we go to the next page, there's one other quick thing that I want to point out on this problem because I think this will happen a couple times in your homework. I just want to point out that this piece of information and this piece of information were absolutely unnecessary. If you are not given the sample mean and if you are not given the sample standard deviation, you would put these values into your calculator under list 1. You'd put this under list 1. You'd do stat, you'd do calc, and you would do one variable statistics. And you would get an entire list including the sample mean, including the sample standard deviation. So all they have to give you is the data. These extra statistics that you were given, the sample mean and the sample standard deviation, it's friendly if you're given that in a problem, but it's absolutely not necessary because we can find that at this point. So what you should do now is pause the video and try, there's really only 2 problems on here, so try these 2 problems and I'll go over them momentarily. So hopefully you've had a chance to try these at this point. The first one says, a company has a new process for manufacturing large artificial sapphires. In a trial run, 37 sapphires are produced. The distribution of weights is approximately normal. Okay, this is a friendly statement, but actually this is a large enough sample size that I don't care. So great that we have it, but we didn't need it for this large of a sample. The mean weight for the sample of 37 sapphires is x bar equals 6.75 carats. And the sample standard deviation is 0.33 carats. Let mu be the population mean of the weights of all sapphires produced. Part A, is it appropriate to use a student's t-distribution to compute a confidence interval for mu? Well, remember the decision tree. So do we know sigma, the population standard deviation? If the answer is yes, you use z, and if the answer is no, you use t. And I'm actually going to add on to this decision tree in section 8.3, so commit that one to memory. Well, in this case, let's see, do we know sigma? No, we don't. We know s. We don't know sigma, we know s. If the answer is no, you will know s. So yes, it is appropriate for me to use t, the student's t distribution, to compute a confidence interval for mu. Also, like I said, the sample size is big enough that we didn't really care if the weights were normally distributed. So all of this is good. Okay, part B, find the degrees of freedom. Well, degrees of freedom is just sample size minus 1. So since our sample size in this problem is 37, our degrees of freedom will be 36. Okay, part C, find the 95% critical value using the table. Okay, so let's flip to our table. We've got two pieces of information that we should take with us. First is the degrees of freedom, and then second is this confidence level that we want. So degrees of freedom 36, confidence 95%. Okay, so let's see, 95% across the top is here, so I'm going to be in this column, and I just need to go down to degrees of freedom 36. Degrees of freedom 36. Well, I noticed that 36 is not in the table, so again we bump it down to the next smaller value, which is 35, and here 2.030 is my critical value. 2.030. T sub 0.95, 2.030. Okay, great. So now we're going to actually find the error. And the formula for the error is, oops, doesn't look like that, is our critical value for t, in this case 95% confidence, times the sample standard deviation over the square root of n, the sample size. And we have everything that we need for this. So t sub 0.95 equals 2.030. S, the sample standard deviation, is 0.33. And square root of n, the sample size, is 37. So square root of 37. Now, I'm going to round this to 2 decimal places. So I'm throwing this in my calculator now, times 0.33 divided by the square root of 37. And I find it says 11013. I'll round to 2 decimal places, so 0.11. Now with that, I'm going to find a 95% confidence interval for the population mean. So plugging into this formula that we keep building on. Remember, at this point now I have x bar that was given to me in the problem. I just found E. I don't plug in anything for mu. I have x bar and I have E. So I have everything that I need. Okay, so everywhere I see an x bar, we're given in the problem that the sample mean is 6.75. So I'll use that there. Minus our error, which we found was 0.11, less than mu, less than, and then same numbers, but now with a plus, 0.11. So when I simplify this, I get what, 6.64 mu is between 6.64 and 6.86. Now I can't say with 100% certainty that the population mean for all of these sapphires that are produced is really between these values, but I can say with 95% confidence that it will be somewhere between 6.64 and 6.86. I don't know if it's exactly halfway between them. I don't know if it's a little bit more on the left. I have no idea, but 95% confident that it's somewhere between 6.64 and 6.86 carats. Good. Okay, number 2 is a little bit more interesting. Suppose a pharmaceutical company wants an estimate of the mean increase in blood pressure of patients who take a new drug. The blood pressure increases for the N equals 6 patients in the human testing phase are as follows. Okay, so these are our 6 data values. That's a very small sample. So this next statement is very important. Assume that the population of blood pressure increases is approximately normal. That's good because 6 is not a big enough sample that we could overlook it if it's not normal. Construct a 95% confidence interval for mu, the mean increase in blood pressure for all patients in the population. Okay, so this is what our confidence interval is going to look like. When you read the phrase confidence interval, this is the formula that you're using every time. So there are a couple things that we need. First of all, we need the sample mean. And I notice in the problem that it was not given to me. So I'm going to take out my calculator. I'm going to go to Stat, and I'm going to go to Edit. And in List 1, so Stat, Edit, in List 1, I'm going to enter these 6 values. 1.7. Okay, so now I've got my list populated with those 6 values. I'm going to go to Stat again, and then I'm going to go Calc and 1 variable statistics. Make sure that your data is coming from list 1 or wherever you just put your data values, and then just click Enter. So when I look at my screen, there's actually a bunch of information on it, but the first thing says X bar equals 2.28 through a bunch of 3s, 3, 3, 3, 3, 3, 3, repeating. Let's see, then it says the sum of x equals 13.7. It says the sum of the x squared, and then it says s sub x equals 0.94956. Okay. There's still a whole bunch of other stuff on there, but really the 2 values that I'm concerned with are the sample mean, because that goes right into my formula, and the standard deviation, sample standard deviation, because I need that for my error formula. So now that I have that, I'm going to use the error formula, t sub c times s over the square root of n. And actually, I just missed a huge question opportunity here. The question is, should I use z or t in this example? And again, I mean, this entire section is about using t, so you are probably pretty safe guessing t, but on the exam, it's not going to be as clear which one you use. So we do need to kind of go through this decision tree again. So for this problem, do we know sigma? Well, the answer is no, we don't know sigma, the population standard deviation. We know S, the sample standard deviation. So no, we do not know sigma. And if your answer is no, you do not know sigma, then you're going to use T. Okay, so we're going to use our T formulas, and that's why I have our T here and not Z. So I need to find, really like kind of the last thing I need to find here is the critical value. So 2 pieces of information go into finding the critical value. The first one is, how confident do I want to be? And the answer to that is 95%. I want 95% confidence. And the other thing that I need to know to find that critical value is, what are my degrees of freedom? And remember, degrees of freedom is just your sample size minus 1. So looking at what I've got here, going back to this problem, if I've got a sample size of 6, I've got 6 values here, then my degrees of freedom are 6 minus 1, so 5. Degrees of freedom 5, confidence level 95%. So I'll bring those over to my table. Degrees of freedom 5 tells me that I'm in this row. Confidence level 95% tells me that I'm in this column, and there is my critical value, 2.571. So I'm going to take that back over and plug this into the error formula. So error equals 2.571, there's my critical value, times S, the standard deviation. I'm going to take this, it doesn't tell me in the problem, but I'm just going to go ahead and round this to 2 decimal places. 0.95 over the square root of n. N is the sample size, so square root of 6. Now careful here, one of the more common mistakes is to plug in the degrees of freedom. You still do use the sample size here, square root of n, so make sure you're using 6 here and not the degrees of freedom. Now when I plug this into my calculator, I'm going to round this to 3 decimal places. I'm finding 0.997. So there's my error, and I'm going to plug that in to my confidence interval. So first of all, everywhere I see an X bar, I'll again round this to 2. Maybe I'll round it to 3 because I've got an error that I rounded to 3. So I'll go 2.283. 283 minus the error, 0.997, is less than mu, which is less than, now again, sample mean, 2.283, plus the error, 0.997. And actually looks like in the answer they rounded it to 4, but whatever, I rounded it to 3. So 2.283 minus 0.997 is 1.286. So I am 95% confident that mu is between 1.286 and 997, 3.28. Okay, so not 100% certain, but I can say with 95% certainty that our population mean is somewhere between these two numbers. This is a fairly large interval from 1.286 to 3.28. I don't really know if the population mean is on one side of that. It might be directly in the middle, but usually that's, unlikely. But I can say with 95% confidence that I think it's somewhere in here. Okay, so we're basically going to do the exact same thing in section 8.3, but for a binomial distribution. So we'll just kind of repeat the exact same process, and actually next time we're still going to be using the student's t distribution. Now if you want an interesting story real quick, this is the end of it, so you don't have to listen to this part if you don't want to, but if you want an interesting story, you might be wondering where or why it's called the student's t distribution. Turns out the student is actually not like you are a student, has nothing to do with like college students or students of any kind. There was a statistician the story goes like this. There was a statistician, he was working for Guinness, the beer company. And of course, when you're producing a product every year, you want it to be consistent. Like you don't want Guinness one year to taste different than Guinness in another year. So they've got this statistician and they're working on like how to make a consistent product. So since he was only dealing with samples and not the population, he did not know the population standard deviation. He only knew the sample standard deviation. And so this guy, I can't remember his name off the top of my head right now, but he came up with this distribution that would help him kind of like pay for the fact that he didn't know the population standard deviation. So he came up with this distribution. And then he knows that this is a really important finding and that other statisticians would want to use this later, like places outside of Guinness would want to use this information like we're using it now. So he goes to the management at Guinness and he says, hey, I want to share this information. I want to like publish what I just found. And they tell him, well, no, you can't share this. It's giving away our, trade secrets. So they come to this compromise and he convinces them that as long as he can publish under a different name, so that basically it's not tied to their company, as long as he can publish under a different name, they will let him share his statistical discovery. And so, apparently not a very creative guy, because of all the names that he could have chosen, he chose to publish under the name student. And so it's a fake name. He came up with the student's T distribution because he had to keep it a secret that he worked for Guinness. Anyway, little gem of knowledge. I will see you in section 8.3.